Chuck Souls. A little history, I was chief engineer of the destroyer Eaton, a 445 class destroyer, and later in my career, chief engineer of the aircraft carrier Midway, a Midway class carrier. The propulsion plants on those two ships and this ship are identical. The equipment in the spaces differs only in size and in location. But other than that, they're a standard 600-pound steam system. Now I'd like to start and talk about the propulsion plant in general. The propulsion plant on any aircraft carrier consumes the middle 1/3 of the total length of the ship down below the 4th deck. The new modern nuclear-powered aircraft carriers, their plants are in the same place. The Navy's is transitioned away from steam power to diesel and gas turbine propulsion. But until somebody invents a better catapult than a steam catapult, our carriers will remain steam powered. Now, I don't care if you use a boiler or a reactor to make steam. Once you have steam formed and you bring it into the engine room, you use it in exactly the same way. Well, let's just talk about the propulsion plant of the USS Hornet, an Essex class carrier. The propulsion plant, the forwardmost space, is a space called forward auxiliary. It has #1 ship service turbo generator and two 50,000 gallon per day each evaporators in it. After the forward auxiliary is #1 fire room. It has #1 and #2 boiler in it. After that is #2 fire room, which has #3 and #4 boiler in it. Then we come to the forward engine room, #1 engine room, the space that we give tours in. There's #1 main engine on that side, #2 ship service turbo generator in the center, and #4 main engine on the port side. After that is #3 fire room with #5 boiler and #6 boiler in it, #3 ship service turbo generator, and #3 evaporator, a 10,000 gallon per day emergency evaporator. Note that in #1 and #2 fire room, the boilers sit side by side. But in #3 and #4 fire room, the boilers sit facing each other. And that's because the ship is getting narrower as it goes aft, and there's not enough room to put two boilers and a ship service turbo generator sitting in an arrangement like they have in #1 and #2 fire room. #4 fire room, #7 boiler, #8 boiler, and #4 ship service turbo generator. And after that is the #2 engine room, the after engine room, with #2 main engine on this side and #3 main engine on that side. The space after that is #2 auxiliary, and it has all sorts of various pumps and compressors, but no direct propulsion related machinery in it. Okay, now I want to talk about the entire propulsion plant and how it works. And so you can, if somebody asks you questions, you can answer them. We start with the boiler. We put feed water, comes into the boiler, and it passes through a device called the economizer, which preheats the feed water. This is an M-type boiler, by the way. The steam enters the generating side of the boiler, and we boil the water and maintain the steam pressure at 600 psi. Water boiling at a temperature at a 600 psi at a temperature of about 489 degrees Fahrenheit. We take the steam physically out of the boiler and we pass it back through the boiler through a superheater. And on this type of ship, we can control the amount of superheat that we pour in the steam. And we raise the steam temperature from 489 to a minimum of 650 degrees if we're going slowly, and if we're going fast, we bring the steam temperature up to 850 degrees Fahrenheit. We superheat the steam for two reasons. One, it gets all the moisture out of the steam so the moisture droplets won't damage the main engines. Then the second reason, we also are adding dramatically more energy to the steam because we're going to use that when we get it into the engine. Now the steam leaves the fire room from the boiler and enters the high pressure turbine. The steam enters at 600 pounds pressure, 650 to 850 degrees Fahrenheit, enters at the front of the turbine, expands aft through the turbine, discharges through a great big pipe, which I'll show you when we get in the plant, called a crossover pipe, and that pressure at high speeds is up on the order of 50 psi. The low pressure turbine is a strange turbine. The steam enters in the middle and expands in both directions, causing that turbine to spin. The low pressure turbine sits on top of the main engine condenser, and we maintain a 29-inch vacuum in the main condenser. The main condenser is a simple device. It has several thousand tubes in it. We pump salt water from the ocean through the main condenser so we can condense the water, the steam back into water so we can reuse it. The water flows out of the main condenser by a pump. The main condensate pump pumps the water, raises the pressure from 29 inches of vacuum to 30 psi, and pumps it back into the deaerating feed heater. And I'll show you all these things when we get down in the plant. The water enters the top of the deaerating feed heater. It comes into a great big spray nozzle at the top and sprays water into the deaerating feed heater. We also take steam that's come off of our steam-driven pumps at about 15 psi called the auxiliary exhaust, and that steam is blown up from the water. So the water's coming down and the steam is coming up, and what it does is heat the water. It heats the water up to about 240 degrees Fahrenheit, and because we're using auxiliary steam, the pressure is at about 15 psi in the DFT. We do that by heating the water droplets. We drive the oxygen that's gotten entrained in the water out of it. We take and we vent the oxygen out through the top of the DFT. This way we prevent the oxygen in the water from attacking the tubes and causing corrosion in the tubes in the boiler. Now, we take the water is pumped out of the DFT, deaerating feed heater, by a main feed booster pump. And this pump takes 15 psi water, increases the pressure to 60 psi, and pumps it back into the fire room to a main feed pump. At low speeds, the main feed pump pressure is at 650 psi. If we're going to be going fast, the guys in the fire room will increase the pressure on this pump to 750 psi to go into the economizer. We keep the pressure at between 650 and 750, so we have a pressure differential above the 600-pound pressure in the boiler, so we can be certain we can force the water back into the boiler so we can start the cycle all over again. All right, we're in the entrance to the forward engine room, also called main engine control. We'll talk about what main engine control means. It's named the mud hole. That means Lieutenant Mudd was the main propulsion assistant, and he must have been a really fine officer that his men wanted to name the space to give it his name. Okay, we're down on the upper level of the forward engine room, #1 engine room of the USS Hornet. The overhead of this space is the 4th deck. That's where the water line is. So we're all standing well below the level of the water in San Francisco Bay. I usually tell the people about the propulsion plant spaces like we talked about. The forward auxiliary, 1 fire room, 2 fire room ahead of us, aft of us, 3 fire room, 4 fire room, and the after engine room, and then aft auxiliary. Okay, we're now, I talked before about we form steam in the fire room, heat the steam to 850 degrees Fahrenheit. So we take steam at 600 pounds, 850 degrees Fahrenheit, and we lead it over to this, which is the high pressure turbine. This series of gears and springs allows the throttleman, as he turns the throttle, to open a series of nozzle valves to very accurately measure the steam coming into the high pressure turbine so he can control the speed. The steam expands aft through this turbine and comes out of that turbine and it comes over through this crossover pipe to the low pressure turbine. Okay, so the steam comes over to this turbine, the low pressure turbine, which is really 2 turbines on 1 shaft, because the steam enters in the middle, expands in both directions, causing this turbine to spin. The steam comes out of this turbine and goes straight down into the main condenser that it's sitting on top of. And remember, I said that we maintain a 29-inch vacuum in the main condenser, and we use it to condense the steam so we can reuse the water. Now these 2 turbines, the high pressure turbine over there and the low pressure turbine here, at full speed, are turning well over 4,000 RPM each. They don't turn the same RPM, but both of them are going well over 4,000 RPM. Way too fast to turn a propeller. So each one of these 2 turbines is attached by a shaft to that big gray box you see back there. That's the main engine reduction gear. And that gear, that's a set of precision gears that takes the input from 2 separate turbines turning well over 4,000 RPM each, gears it down to drive a great big gear called the bull gear, which is about 6 feet in diameter and buried in the center of that gear. And the bull gear is what's bolted to the propeller shaft. And at full speed, that propeller shaft and that propeller is turning 251 RPM. This main engine is 37,500 horsepower. There are 4 37,500 horsepower turbines on this ship for a total of 150,000 horsepower, capable of pushing this ship at speeds up to 32 knots. The big new nuclear powered carriers that are more than twice the size of this ship require 260,000 horsepower, and they can't go any faster than the Hornet could. Okay, somebody's going to ask you who Shirley was, and I'm not really certain. Shirley might have been the wife of somebody who worked down here, but she just as easily could be a lady of less than perfect repute that the sailors knew on the beach. And that's all I can tell you about Shirley. All right, now this red and white painted device here is the propulsion shaft. It's about 18 inches in diameter, and it's painted red and white so we can tell which way it's turning, and for other reasons, which I'll talk about when we get over to the throttle board. Okay, this is number 2 ship service turbo generator. It works just like the main engine. Steam comes in here at 600 pounds into this turbine, expands aft through the turbine, causing it to spin. It drives through a small reduction gear here to drive the generator, which is in this big box. This generator is capable of generating 450 volts, 60 cycle, 1250 kilowatts of power. The ship has 4 1250 kilowatt generators. And in World War II, that was a lot of electrical power. But now, because we have so many electronic devices and other big things on our much bigger ships, the big nuclear powered carriers today have 8 2500 kW generators, and already are people wondering, are we going to have enough power? Okay, we're at the throttle board. Your red light didn't come on. Okay, we're at the throttle board of the USS Hornet. Number one main engine. This is the ahead throttle and this is the astern throttle. Now, the person who operates these throttles are called the throttleman. Now, talk about on the bridge, you'll see when you get up there, you will see an engine order telegraph, and that's a brass device, stands about this high, and it has two handles on it. And the guy on the bridge, when the officer of the deck tells him to, the lee helm, tells him to change the engine speed, the kid will go back and forth with these two handles. This handle gives orders to the starboard engines. This handle gives orders to the port engines. And the reason he's going back and forth is he wants this bell right here to ring more than once, because it was noisy down here. Now, in the old days, we just, all right, get your tail down in the plant and go to work, and we did. And many of us today are wearing hearing aids, like I am, because of it. The modern Navy, if we were steaming, you wouldn't have been allowed to leave the fourth deck to come down here if you didn't have hearing protection on. Okay, so the kid on these throttles, here's the bell ring. And he sees, this is his engine of the engine order telegraph. And he sees the little arrow that he had on 2/3 is now alone, because the bridge's big arrow is pointing at flank. And all he's got to do is match pointers. He doesn't have to spin it back and forth to make it ring more than once up on a bridge, because it's supposed to be quiet like a church up there, and if it isn't, I couldn't possibly explain it from down here. Okay, now the officer of the deck could also have given a well, the major speeds here are stop, 1/3, 2/3, standard, full, and flank. 1/3 is 5 knots, 2/3 is 10, standard is 15, full is 20, flank is 25. And sometimes you may hear somebody talking about the ship went all ahead Bendix. Well, it just happens to be, if you go one more click, you'll find the Bendix logo down there, and that's what all ahead Bendix means. Okay, but let's say instead of going 25 knots, the bridge wants to go to a different speed. Then the officer of the deck, hey, he wants to go 27 knots, and he would tell the lee helm, indicate turns for 27 knots. The kid on the bridge would punch his table. Okay, so the officer of the deck says he wants to go 24 knots instead of 25 knots. So the kid on the bridge would go to his table, and 24 knots is 182 RPM, it says. So he would go to his engine revolution indicator on the bridge and go to 184. That causes a bell to ring down here. And the numbers on the top would go to 184. So the kid down here goes to 184 down here. And what do you know? It causes a bell to ring up on the bridge. And his numbers on the top go to 184. So he knows that we know that they want us to go 184 RPM. Why 184 RPM? Well, we built the carrier Essex, the first carrier of this series. Took it out and played with it and discovered all 4 shafts turning 184 RPM. The sucker goes 12 knots. It goes 24 knots. So you make it a table and you give it to everybody else. Now, of course, when we built the Hornet, we had to take her out and make sure the thing, it was exactly right. But it gave us a good starting point. Oh. Now the throttleman, when that bell rings, we expect him to perform a minor miracle. The bell rings, he's supposed to look up here and see what time it is. The clock disappeared about 30 years ago, but that's where the clock used to be. He's supposed to look at that, remember that. There's a counter here that tells you counts every time the shaft turns. So he's supposed to look at that counter, remember that, operate this, open or close the throttles as appropriate, and then on a clipboard mounted right here is a piece of paper called a bell sheet. One of the 2 legal records maintained aboard ship. The other legal record's up on the bridge. And he's supposed to write all that information down, and we prefer him to do it at the same time. It has to be done quickly, must be done accurately. If he makes a mistake on the bell sheet, he has to line it out and write in the proper entry underneath it. He cannot erase it. The next day, his chief, when he reviews the bell sheet, will see, gosh, fireman so-and-so screwed up the bell sheet. So he may very well have this kid sit down and rewrite the entire 24-hour long bell sheet with no errors in it, take it around and get everybody who signed it to sign it. And this usually focuses the kid's attention on, let's do it right the first time. Okay, now you're bound to get asked what some of these other valves are. This valve right here is the main engine guarding valve. The guarding valve is normally closed when you're in port and steaming in port. And the purpose of the guarding valve is to keep steam away from the high pressure turbine throttles, the throttles on the turbine, because those nozzle valves have a tendency to leak by, and you don't want steam into that engine until you're ready for it. So this valve, the guarding valve, is only open just prior to getting underway. People will ask you sometimes, what's this red valve? This red valve allows you to bypass some steam around the stern throttle valve to equalize the pressure on either side to make it easier to open or close the stern throttle valve. But normally the red valve is closed, and going ahead, of course, the stern throttle is closed. Now, okay, now the throttleman, you're going along, the worst possible casualty you can have is in the engine room is to lose lubricating oil to your engine and your reduction gear. If the pressure starts to drop in that system down low enough, that red siren down there will go off, and it's like waking the dead when that thing goes off. And that tells this kid he has to close the head throttle and open the stern throttle and dump substantial steam into the stern stern turbine to make the ship to stop the shaft. I didn't show it to you, but on each end of the low pressure turbine there are two pipes coming down labeled the stern steam, and that's because there's a couple of rows of blades on each end of the low pressure turbine that are in backwards. You've got maybe 60,000 horsepower going astern, but that's enough to allow you to slow the shaft. Now, what the kid does is he opens it, the head throttle is closed, and he's open his stern throttle, and he's looking back through this window, and if you see back there, there's a red arrow with the pointing that way, and right above it the words ahead. Now what he's doing, and if you look above the arrow, you can see a red and white stripes of the propeller shaft. Now if we're going any speed, that propeller shaft is a pink blur. But as the kid opens the throttle more, that pink blur will slow and it turn into red and white stripes turning this way. And he'll add a little bit more stern steam to what it stops. And his job is to keep it from turning. And the top watch and the messenger of the watch are back on top of the reduction gear, getting ready to engage the jacking gear so they can lock that shaft so it won't turn. Once they tell him that they've got the shaft locked, the kid can then close the stern throttle, and the shift is, and then we can start trying to figure out what damage, if any, we did to the reduction gears. Now this kid on these throttles can do a unique thing. He can turn the lights out in this part of the ship just like that. Now the bridge has just said they want to go flank speed. Now they just ordered this kid to open this throttle and dump substantially more steam into that turbine to make it turn faster to push the ship faster. Not a problem in the engine room. The problem's on the other side of this bulkhead, number 2 fire room. Number 2 fire room feeds this engine. number 1 fire room feeds number 4 engine. And before this thing goes from 2/3 to flank, those guys in number 2 fire room have those boilers set up beautifully. They're at 600 pounds pressure, 850 degrees Fahrenheit superheat, and they're generating just enough steam to drive this engine at 2/3 and a little bit more steam for that ship service turbo generator sitting over there. So, if this kid, as soon as he starts to open this throttle, the steam pressure is going to drop in this fire room. And when he goes from 2/3 to flank with this, a repeater just like this in the fire room goes from 2/3 to flank, and those guys are busier than a one-arm paper hanger in that fire room. They're lighting off more burners. They're taking burners that were in that have little tiny sprayer plates out, putting in bigger burners so they can force more oil into the boiler. They're increasing the fuel oil service pressure at the face of the boiler to get more oil into the boiler to be burned. They're increasing the speed of the forced draft blowers to blow more air into the boilers so you don't make smoke. If you don't have enough air, you smoke black. If you have too much air, you smoke white. And those guys are scrambling to get those boilers to generate substantially more steam. Now it's going to take several minutes to get that to happen. If this dummy just pulls, as he opens the throttle, if he pulls that steam pressure down to 550 psi, the guys in the fire room says, hey, that fool's about to burn up my boiler, I got to protect my boiler. How do you do that? Why, you secure fires and close the steam stops. And all of a sudden it gets slow and dark down here because there's no steam. And somebody standing right about where this gentleman over here is standing would come over and start reasoning with this young man and pointing out certain shortcomings in his behavior, probably forcefully. Because he shouldn't pull that pressure below 585. Those BTs will get that boiler, those boilers going faster, and we'll get the pressure back up, and if we get it up, as it comes up, the pressure will start coming above 585. So the kid can add a little bit more into the engine as he watches his RPM come up to the ordered RPM. And about the time he's up there, they got the boilers nearly up to speed, and we're on track. Now, we're chugging along at 25 knots, and our good friends on the bridge, bless their hearts, they want to go 10 knots again. You got no choice. You got to close the head throttle. And that poor little old generator over there can't eat 25 knots worth of steam out of 2 boilers. So those guys in number 2 fire room are every bit as busy as they were before. Now they got to make their boiler not use so much steam, generate so much steam. And what happens now, the steam pressure is going the other way. It's going to go, and if it goes up high enough, it's going to lift the safety valves on the boilers. If you ever worked around safety valves, you know every once in a while they're going to stick in the open position. And if they do that, you've got no choice. You've got to secure the boiler. And then listen to a terrible sound, and that's the sound of a 600-pound boiler screaming from 600 pounds down to 0 through that defective valve. It'll take 8 to 12 hours depending on how hot that boiler was. And I say, and if you like boilers, it's a terrible sound. And then once you get it down to 0, you let it sit for a couple more hours, and then you hand some poor devil a wrench and invite him to climb up on top of that nice super hot boiler at the hottest part of the fire room and unbolt that valve that's mounted on top of the boiler and replace it with a new one. You don't want to do that. And the kid on these throttles can prevent that. As he sees the steam pressure going above 600 pounds, he's already got his head throttle closed. Open the astern throttle and pull steam off the boilers and dump it into the astern throttle. If you're going like 25 knots, there's no way you're going to stop that shaft and make it turn in the opposite direction by opening the stern throttle. All you're doing is accelerating the rate at which the shaft is slowing. And when you get it down, so the kid I'd open this throttle and I'd pull that steam pressure down to 605. And as those guys in the fire room get their boiler generating capacity to start to drop, the pressure here will start to drop below 605. So I close the throttle just a little bit and keep it at 605. And watch the RPM indication drop off. And as we get close to 2/3 speed, the kit they'll have the boiler generating capacity down to about what it ought to be. The kid can close the astern throttle, open the ahead throttle, and answer his bell. It's a good example of what happens throughout our military, where you've got groups of guys that can't see each other. They don't have the world's greatest communications with each other, but they have to work very closely together in a coordinated manner. So I get asked occasionally, does it get hot down here? And the simple answer is yes. But if we were steaming today in San Francisco Bay, where the air temperature topside is in the order in the 60s, that salt water temperature out there is around less than 55 degrees Fahrenheit. So it would be nice steaming down here. It would be 70, 75 maybe. But this summer, we've had ships operating in the eastern Mediterranean, supporting what's going on in Iraq. And just like we did when we operated in the South China Sea during the Vietnam War, that salt water in those areas in the summertime is 85 degrees. The air temperature topside is in excess of 85 degrees, and you can get temperatures down here 105, 110 routinely. Upper levels of fire rooms where fortunately sailors don't have to stand watches. I've seen it between 130 and 150. So you don't want to stay there very long. Okay, I'll just talk, you might be asked what some of this stuff is. This device right here and all these gauges and valves are associated with the #1 main engine air ejector. This is the Bernoulli tube type air ejector that's taking a suction on the top of the main condenser to create the 29-inch vacuum in the main condenser. Down here is the top of the main circulating pump, and that's the pump at low speeds, and when we're getting ready to get underway, that pumps water through the main condenser to condense that's pumping salt water to condense the steam back into water. Now, this valve here is the bulkhead cutout for main steam coming out of #2 fire room. The steam from #2 fire room comes in through this valve, so we can bring it into this engine room. Okay, this right here is these are, well, in the Navy I served in, these were called bitch boxes. They have a different term. But these are ways that the engineering officer of the watch, and I'll tell you about him in just a minute, would use to communicate with the bridge and primary flight control and the repair parties, the other fire rooms, to communicate with them. He also has what was called a J-dial, or standard dial telephone. It's very difficult to use with all the noise level down here. Now, people also will look and say, why do you have a gyro repeater down here? And that's because the chief engineer is responsible for the gyro. And this might be the first indication, if you see this starting to spin, that something's gone wrong with the gyro, so the officer of the watch can call and get people working on solving that problem. These devices right here measure the amount of salt in the condensate. You know, when we condense the steam back into water, it's called condensate. And if the main condenser saltwater side is leaking into the the condensate side, these measure that and will detect it. Because you don't want salt water in your condensate, because you don't want to put that in your boiler, so that too can cause problems in your boiler. And I'd like to talk about the engineering officer of the watch. Like from this point in the throttle board over that way. That throttle board is very similar to the other 3 throttle boards, with the exception that up on top you have the RPM indication from the other 3 main engines. And that's because the officer of the watch stands his watch over here. So with that information over there, he has a pretty good idea what's happening with the engines. Now boilers are harder to figure out, so he needs more information. This funny looking thing tells him the air pressure in each of the 8 boilers. Here's your main steam pressure in all 8 boilers. Here's the fuel oil service pressure in all 8 boilers. And I showed you on the graph, on that diagram, that the water is pumped back into boilers by using main feed pumps. Well, there's the main feed pressure in each of the 8 boilers, each of the 4 fire rooms, excuse me. Now, the officer of the watch's job is to coordinate what's going, this is what makes this called main control, because the officer of the watch stands his watch down here. Now the officer of the watch is a junior officer in the engineering department, or he may be a senior chief or a master chief boiler tender, or a master chief machinist mate. Now, their job is to give orders to the other portions of the propulsion plant necessary if an alarm goes. Like I say, if this alarm went off, he would immediately notify the other spaces that they have a loss of lube oil, #1 main engine. And now if we were going faster than 15 knots, he'd have to call the officer of the deck and request an emergency standard bell because of a loss of lube oil in #1 main engine. So the officer of the deck would have to give an order to slow all of the engines down, because if the whole ship is going faster than 15 knots, you can't stop this shaft. So that gives the guys here a chance to stop it. So the officer of the watch is very important to give the orders. He has to tell everybody what they need to do and make sure all 8 spaces are operating in a coordinated manner. Okay, now if you're an engineer, you're always interested in how much wind is blowing topside, because for every airplane in the air wing, there's a minimum amount of wind that has to be blowing over the deck of the ship to safely launch the aircraft, and another to safely recover the aircraft. Now, I don't know what the numbers were on this ship, but on my carrier, the Midway, it was 28 knots. Now Midway is a 12 boiler ship, but we could just make 28 knots with 8 boilers on the line. And if you're an engineer, you say you're always hoping the good Lord's providing plenty of wind, because if he isn't, and there is no wind, you make that speed down here, and that's important. Now, one thing I didn't cover is that each one of these main engines has bolted to it a propeller shaft. The propeller shaft's about 18 inches in diameter, and for #1 and #4 main engines, those propeller shafts leave this engine room and go aft inside the ship through 3 fire room, 4 fire room, the after engine room, and those 2 shafts leave the interior of the ship in aft auxiliary. Those shafts continue aft to just about the end of the hangar bay, and they're supported underwater with strut bearings. The #2 and #3 main engines aren't nearly as long. They go through aft auxiliary and through one more set of interior spaces, and then they come out, leave the interior of the ship, led aft underwater, supported by strut bearings, to about the end of the hangar bay. Alright, so each one of those 4 propeller shafts, each has its own 15-foot in diameter propeller, which is used to push, to move the ship. Just a couple of other things. Unique to main control, there are these boards here where you can keep track of which valves are open or which valves are closed, and this gives the officer of the watch more information that he needs, particularly when something is changed and a new guy's coming on watch. You can brief him on what valves are open and what are closed. All right, this is number 1 deaerating feed tank. This is the tank I told you about where we spray the water in the top and spray steam up from the bottom. And the spray nozzles for the water coming in, the condensate coming in is up, you can't see it, but it's up above that level. And so the droplets of rain come down and the steam comes up, and we maintain about 3,000 gallons of hot water in this tank. Both engines feed into this one tank. This device right here is known, can you show it in here? This is called the Here booth, and if you really need to make an important telephone call, you can come in here and the sound deadens so you can use it. This is similar to the 1MC up on the quarterdeck, but this is called the 2MC, where you can turn off the topside switches and just transmit announcements to the propulsion plant spaces. So this isn't used very often, but it's very, very handy. Okay, this is the throttle board for number 4 main engine. You can see it's dramatically different from the one in the number 1 engine side, because it doesn't have all the main control gauges and information on the boilers, and that's because just the throttleman stands his watch over here, and all he has is the stuff that he needs so he can do his job to run number 4 main engine. This is the throttle, this is the bulkhead stop for steam coming in for number 1 fire room to feed this engine. And again, he has his air ejector condenser to maintain the vacuum on the main number 4 main condenser. Okay, this is the lower level of the engine room where you don't take tourists, but I want to at least show you some of the equipment down here so you have a better feel for the engine room. Okay, we're over in the Lube Oil Flats area of the Hornet on number 1 main engine. Now, the ship has been severely cannibalized. Because she had hydraulic cats, she was one of the first carriers of the Essex class that were put out of commission, and we kept other ones that had steam catapults much longer. And as they needed parts and you couldn't find anybody who could make them anymore, you came aboard carriers like the Hornet and you stole it. The electric lube oil, main lube oil pump was in this hole. Now here's the steam lube oil pump. The ship normally had an electric and a steam lube oil pump, and at low speeds, one of these other pumps would be on the line. You'd set it up so one of them would be delivering 15 pounds of oil pressure at the furthest bearing. It's called the most remote bearing. So you adjust everything to make sure that that bearing's getting at least 15 pounds pressure of oil, and the other bearings are getting more. If you had it set up so the steam pump was doing that and something went wrong and this pump malfunctioned and starts delivering less pressure, the electric lube oil pump would come online and provide oil to keep the ship going. If both pumps failed, that's when that red siren up there went off and you got the alarm for loss of lube oil. Now at very high speeds, this is a chain that is underneath this cover going up attached to the propeller shaft, and this is a chain drive lube oil pump. And at very high speeds, this lube oil pump would take over and these other 2 pumps would go into standby while this one provides the power. It's a pretty slick thing. I was on the destroyer one time, though. We were going at flanks at full speed, turns for about 36 knots, when that chain in the number 2 engine, I got word the one in number 2 engine room was acting up. And my chief and I were standing down there looking at it when the chain started to come off that pump. And if I'd moved any slower, that chief would have run right over the top of me, because we had to stop and lock and get that fixed. Okay, now the water, you've condensed the water into the main condenser, and you want to pump it out of here into the deaerating tank. Here's a steam-driven condensate pump, and there's an electric condensate pump. And we'd use those two pumps to pump the water up into the main condenser. The faster, if you go at really high speed, you'd have both pumps on. Normally, under 20 some odd knots, you would only have one pump on the line. But you got a kid on watch down here, and his job is to mind these pumps. I talked about the main circ pump when we were on the upper level. Well, there's the bottom half of the main circ pump. And it's taking a suction on the ocean and pumping the water into the main condenser. Now, that's a big pump and it eats a lot of steam, and one of the ways we can be more efficient is we've taken a pipe and put it so it is pointing forward. And if we open this valve here and the ship's going fast enough, like over 5 knots, there's water being scooped out of the ocean and up into the main condenser. This is called a scoop injection. And at any normal speed, you're scooping water into the main condenser and you're keeping the main condenser cool so you can put the main circ pump on standby. Okay, here's the bottom of the DFT right here. And the water comes down out of the DFT and it goes over to missing pumps. This is where the main feed booster pumps would be. That would be taking a suction and pumping the water back into the fire room so they can reuse it. There's one steam and one electric booster pump for number 1 main engine, and there's another steam and electric pump for number 4 main engine. All right, we're down in number 2 fire room. I won't specify which boiler we're talking about because both boilers have the same function. In here, this is the manhole cover, access to the economizer. The hot air, the fumes from the fires come through the generating bank and come up through the economizer and right straight on up through a ductwork that takes it all the way up to the top of the stack as the smoke is leaving the ship. I talked during the briefing about guys in the fire room wanting to make sure that they aren't making smoke. Well, this is a periscope and that's a periscope. And the guys on the lower level are watching. There's a light in the economizer and they're watching to see what color smoke is going up the stack, and that's how they can adjust the force draft blower. Now, why don't you come over and just show the folks. Those are just finned tubes that the feed water that's coming into the boiler is going through to get preheated before we put it in the boiler. Just like the name says, it's an economizer and it makes the boiler more economic. Okay, now you're getting ready to put the feed water into the boiler. So it comes over to the check valves, which you use to regulate the amount of water going into the boilers. And if everything is working right, the guys it's being automatically handled. If you have a problem with your automatic system, some poor devil has to stand his watch up here and manually operate that valve. And he's looking. These are the gauge glasses, and he's looking at the water level, and he wants to keep the water level right about there. That's about halfway across in the steam drum. This is the steam drum. It's hard to see them, but right up there right up there on top of the main steam drum are the safety valves that would lift to protect the boiler. And that's it for this. Okay, this is where the fire pumps were. They are the main feed pumps. They took them off to give them to another ship, but this is where the main feed pumps were. This ship originally had 8 of them, and there's 1 of them left in one of the after 2 fire rooms. I don't remember which one, but they're probably still here because it didn't work anyway. Okay, this is a saturated furnace. This is where we generate the steam. And these are the various burners that we would use to heat the oil. A burner barrel with a sprayer plate in the end would be inserted in here. The other end of the burner barrel comes there. You take it in, dog it down, and when you want to light it off, you just open this valve, and that'll allow oil to spray in through this burner. There, above here, up in this area here, that's the mud drum there, right here. This is the mud drum, and steam generating tubes, so about 5,000 of them, come from the steam drum down and plug into that steam drum, the mud drum. The heat generated in here goes up through that bank of tubes and then on up through the economizer and out of the fire room. The steam we generate in the generating bank, we take physically out of the boiler and we take it around to the back of the boiler and we put it into a superheater, the superheater. You can actually see in here some of the superheater tubes. What happens is that it comes in at the bottom, circulates through, goes up, circulates again, up, circulates again, 4 times. And in this
Wait a minute.
furnace...
Okay, start again.
Okay, this is the superheater furnace, and this is the furnace we use to raise the steam temperature from 489 degrees up to a minimum of 650 and a maximum of 850 degrees Fahrenheit. The burners work just like the burners over there, and you control it through here. The steam, the hot air from here passes through the superheater bank, through the generating bank, and then up to the top of the boiler as it goes out. Now, people, you may have heard about you need to blow tubes. Well, this is a soot blower. And what happens when you're going to blow tubes, first there's soot blowers up in the economizer, and you blow those first. And all you do is just put steam into here and you turn a crank, and what that does is revolve a pipe with holes in it, and that pipe, those holes, you let steam in there to blow the soot off of the tubes as much as you can. So you blow the economizer, you come down here, and you start low and you blow sequentially up and blow the economizer last to get the last of the soot out. People will say, what kind of fuel did you burn? In World War II, the ship was designed to burn Navy Standard fuel oil, which is an oil that's been distilled maybe once, and or bunker C, which is commercial oil that essentially comes right out of the ground. And it's bunker C, and when it's cold, you can shovel it faster than you can pump it. So when you put bunker C down in your fuel oil storage tanks on the ship actually has steam piping rigged through all of those tanks so that if they've got bunker C, they can run steam through there so they can heat the oil enough so they can pump it into the ready service tanks for the fire rooms. Now, Navy Standard fuel oil was a black oil, and you still had to heat it to get it to burn properly. You'd heat it up to about 350 degrees Fahrenheit. and it was a dirty oil, and it left a lot of soot on your tubes. So every 600 steaming hours, and that doesn't take very long when you're steaming 24 hours a day, every 600 hours you have to secure your boiler, let it cool, take all the side panels off, and go in with big steel rakes and brushes and scrape the soot remaining off the tubes. And it takes your nice clean fire room and turns it into a trash pit. It's awful. Well, just about the time they were putting Hornet out of commission, the Navy shifted the ships we were going to keep to JP5. Burning JP5. That's a diesel-like oil, and you could burn about every 1,800 hours. You had to secure your boilers, take the covers off, and go in with whisk brooms and tidy up. It wasn't no difference. Anybody who steamed black oil ships and JP5 fueled ships would never in their right mind go back to Navy standard fuel. I've done it both, and there's no question on my mind. The problem is Navy standard fuel oil. If I want a butt kit down here, all I got to do is take a number 10 coffee can, put 2 inches of Navy standard fuel oil in the bottom, and I can throw anything burning I want to into that, and it'll put it out. JP5, on the other hand, if one of these flange surfaces sprung a leak and that spray of oil came out and hit anything hot, you're going to have a fire. So you've got to really have well-trained crews in firefighting on what to do, but nobody would ever want to go back to Navy standard fuel.